Hello, class of Comp 232. I have actually received a lot of comments concerning your exam. I have noted that it's on Friday the 17th, but looks like you all would rather have it at the 24th. There was some misunderstanding, so let's set the date now, and I will send you a notification that your exam is going to be on Friday, the 24th. Okay, so it's going to be Friday the 24th for the midterm, which is exam one, and you're going to have a project presentation on Wednesday, May 13th, because your grade out of 60 has to be ready by Friday, May 15th. So let's save the date. You're going to have the project presentations. I'm going to have Zoom presentations. I will share with you the topic of the project, and it's going to be handed in on May 13th. Your exam is going to be Friday the 24th. We still have, let's say, 3 or 4 topics that we should finish. Okay, we're good on time. If anybody has any comment, you are free to send me an email, and I will do announcement with the project and with the exam one. The final will be done in the final period. All right. Now let's continue with our topic for this week, which is about trees. I have introduced trees. Now we know what a root is, what leaves are. That's what you should know. We should know the depth. The depth, we know that node A is at depth 0. All these nodes are at depth 1, and all these nodes are on depth 2, and we say that the tree has a depth of 2. Okay, that's what really interests us, and what interests us in trees in general is the number of edges to go from the root to a leaf. Okay, so this is 2, and this represents the height or the depth of our tree. All right, so I guess we stopped here, and now we're going to learn about traversals of tree traversals. So there are some topics in trees that are interesting, straightforward. We're going to take the pseudocode, which means the algorithm of these functions, and then you will be asked to implement them and send it to me, and I'm going to grade the implementation that you do. You can do it in the lab and send me the assignment by email to me and Ms. Hoda. So what do we have here? In here we have something called the expression tree, and this is how the expressions are done by your compiler, by the language compiler. And that tree traversals shows how to create the lexical analyzer, which shows the order by which they're going to appear. So this is how they appear, and how to do this is by creating this tree. And there's a way of traversing this tree. In this example, in the arithmetic expression, what you start with is a child. Okay, so this is A. The traversal is child, root, child. Okay, so if you have the root is plus, right? You don't write it down. You go to this plus. You don't write it down. You start with the child. Okay, so you always start with the leftmost child. So the child here is A. Then the root, which is plus. Now there's another. This is another. The node, which is the parent. In here you have a parent node as well. You start with the left child. So B. You see. B, and then the parent, and then the child. Okay, so this is a way of traversal of trees. Now that we have finished all the left hand side tree, now we put the parent, which is plus, in here. Okay, now for the plus, this node here, this parent node, we look at its left child. The left child is itself a parent, so we look at its left child. The left child is as well a parent, so we look at its left child, we write D. And that's what happens here. Then we put the parent, and this times multiply. Then the right child, E. So now we have finished the left child, the left subtree of this node. Now we can put it plus. Now the right child, which is what? F. At F, we have finished all the left subtree of this node. Now we put this node, we visit the node, and then we visit the rightmost tree. And by this, we have traversed this tree, and this is the tree that corresponds to this expression. Trees are used a lot in the lexical analyzers or in the different parts of your language compiler. We will visit traversal of tree in a minute. Now let's look on how to add a child to a tree. So we want to create a new child node. Okay, to add it to the tree, we add a pointer. So how do I add a child to a tree? The same way as let us recall what we took in the different data structures, stacks, queues, and linked lists. We learned how to add nodes to the tree, to the data structure, to push nodes to the data structure. So now I want to push a node to the tree. So to add a node to the tree, you create the node and then you add a pointer to this node. So I add the pointer to this node in the linked list of child pointers and the corresponding parent node. So add a pointer to this child in the linked list of its parent, simply. So for example, if I want to add a new child called F to B, then I'm going to add a pointer to F in the linked, somewhere in the linked list at a certain position. And as you have seen in linked list, I can add a node anywhere in the linked list that I specify at index k, as you still remember, and I hope you do, and I hope you are studying. All right, so at an index, at any index, I can add a node. So to add it, I just add a pointer to it, and in this way you have pushed a node to the tree. Now how to delete a node from the tree? So as we did with every data structure, we want to learn how to add and how to delete. So in this example, we want to delete a child of B. So to do that, no, I want to delete B, the node B. So deletion of a child B. B is a child of the root. Okay, so I want to delete node B. So to be able to delete a node, the first step that we do is that we have the children of this node. Okay, we want it to be the children of the parent of B. Very simple. So I add pointers to E and to F, which is the linked list that's present in node B. I have to insert it in the linked list of its parent, in this case A. So A will have C and D as children, as well as E and F. So very simple. The linked list of pointers that was present in B, I'm going to add them to the linked list of children of A. And we free the node B. And this is how the tree now is going to look like. That was the deletion of a child. Now, if I want to delete the root, what should I do? One of the children of the root is going to become the new root. So in this case, we select any of the children. Let's say C. Now C is going to be the parent. And what happens? C is going to replace its parent, so C will become the root. And what happens to its children? The children of this node, okay, will stay with C. And C. So how to do that? C will have its child, which is G. It still has its child G in its linked list. But what do? Obviously, we add to it pointers to B and D. So we add to it the linked list of the children of B, pointers to B and pointers to D that was in the linked list of pointers of node A. So C will have a pointer to B in its linked list, a pointer to its already present child G, and a pointer to D. So this was about insertion and deletion to a tree, any tree. We will see later on that we have different types of tree with restrictions on the values. We haven't talked about that yet. Now, so this is generally speaking. Now, tree traversals, as I said before, we have different types of traversals. We have the pre-ordered traversal and post-ordered traversal. What's a pre-ordered traversal? So first, we visit. Okay, so first do the required operation with a node, then with its children. That's not what we did before, right? We did that of the left child, then we visited the root, the parent, and then we visited the right child. In the pre-order, what you do is that first you visit the node, the parent, and then you visit its children. So first you have to finish with the node, and then you go to its children. In post order, first we do the required operation with the children, then return to the node. So that's pre-order and post-order. Let's look at them. So for example, we can use a certain type of traversals in order to print out the data in a tree in a certain order. So in a pre-order traversal, we print the data at the root, pre-order. You can memorize it like this, pre-order, so first do the root. And then you recursively print out all the data in the leftmost tree and recursively print out all the data in the rightmost tree. Why? Because we have to first do the operation on the root and then on the children. That's what we said here. First on the root and then on the children. But the child itself, but the root, the child of the root, the left child is already a tree. Let me give you an example here. So this is the root, right? So we're saying visit the root, visit it, and then visit the children. So I come to visit the child B, but B is also a tree. It's a subtree. So I have to visit B and then visit its children. So you have to print A. You come to the children, you have to visit B and then its children before you visit C. Because B is actually another tree. So how do I visit a tree? Parent, then its children, E. So I visit E is a parent. Oh, it's not a parent. It doesn't have any children, so I stop here. We stop at E. I have to finish up with B's children. So I visit F. Check, does it have any children? No. So I stop here. B has another child, which is G. So I print G, no children. I stop here. Now that I finished with this child of A, now I go to the second child, which is C. To visit C, C is also a tree. So how do I deal with the tree? I visit the root of the tree, the root of this subtree, which is C, first, and then its children. This is the child. Is it a subtree? No, it's just a node, so I just print it. Or you can say this is another subtree, but it doesn't have any children, so you just print the parent. Now A has another child, which is D. So I'm finishing up with the children of A, but if the children, because the child of A is also a tree, so I have to pre-order this tree. So I visit B, the root, and its children. If this child is also a subtree, then I have to visit the node, that is visit, in this case, let's say print, and then its children, etc. So finally, we finished with B, with C, now D. I want to finish up with the children of my root A, but D is a subtree. So how do I do with it? Also pre-order, visit pre-order of this subtree. So what's the pre-order? What does the pre-order tell me? Pre-order. So first the root, then the children. So I finished up with the root, then I printed. So I got the left child, it doesn't have any leaves, so I print I. The second child, no leaves, I print J. And in this case, you have printed, this is the printing of the tree using pre-order. Alright, such questions might come to the exam where you are asked to either write the code okay, or traverse the tree using pre-order. So if you traverse the way I told you, you will get this printing on the screen. A, then B, then the children of B, which are E, F, G, the second child C, its child H, the third child D, and its children I and J. How is it done in the pseudocode? The same way I discussed it, which is recursive, which means that to visit a node, so I start with this function, visit a node. So always in trees, you visit the root, and then from the root, this function, if you call it once, it will visit all the elements in the tree. Again, to visit, to print all the elements of the tree, okay, I call visit node, which is A. So if you visit the pointer to A, if you call function visit pointer to A, then, okay, all the nodes are going to be visited. In this case, visiting is doing a printing. It could be doing anything else. It could be incrementing. It could be doing any function. In this case, we're just printing. So when I visit a node, what's the first thing that I do? I print this node, okay, being supposed to be a parent. So I print this node, which is a parent, which is the root. Okay. Then for each child, I loop. What do you mean? What do I mean by for each child? When I say for each child, so this is a for loop that contains each child of my node A. What are each child of my node A? Let me check. Do I have a pen here? This is a pen. I hope it has good precision. Okay, so the 4 here, I have B, C, and D. Okay, every 4, as we all know, when I say 4, this means it's already determined. The nodes are already determined. How many nodes am I? How many times am I going to do the iteration? So when I say, whenever you see a for loop, this means there's a definite number of iterations in a for loop. In this case, it has to go through B, C, and D. It starts with the first iteration, which is on B. It goes and visit what? C is a variable here. We say C for child. So C is equal to B. So visit B. To visit B, this is a recursive call. Okay, nothing happened here. So it's a recursive call to this function. Okay, so it's going to visit node B the same way it did with A. So in B, when I call B, it's going to have a for loop. It will have a for loop that will contain E, F, and G, the same way I discussed it. Okay, so it will have E, F, and G. When it finishes with E, F, and G, okay, when it goes to E, now in the for loop of B, I have 3 iterations, E, F, and G. On E, for each child of E, what will I have? How many children? 0. So what does the for do? End for. The for will end here. So this is the first ending of the iteration. So this iteration ended. Okay. E, it prints the nodes. How's the function going? Print the node and then look at its children. Okay, so we printed A, we're looking at its children, B. We printed B again, you call the function visit. So we print B, we look at its children. And we print E, we look at its children, but there's no children, so we stop. This one finished. So we finished this iteration, this looping, this recursion finished here. F, you print F, when you call visit F, you print F, and then you look at its children. No children, 0 children. Okay, so this one will end, the iteration here will print F, and then it will end. It's very smart, the F is very smart doing relations in my drawings. So F, it will end here, okay? G doesn't have any children, no for loop, so it will end, the function will end simply if you traverse it. Print F, no children, for, having no children, no for, so it will end. So here also, the recursion will end F, here the recursion will end G. Once the recursion E, F, G, and so the for loop of B ended. Now we ended the for loop of B at this point. Okay, now we continue with the second child in the for, which is C. Okay, so now with C, you print C, visit C, and then for each child of C, child C, I said it's like I, it's like a variable. So for each child of C, what child of C do we have? I have only H. So I go to each child, I do a recursion. Okay, visit H. So I go visit H, I print H, and I'm going to look in the for loop at the children of H, but there's no children, so the recursion of H ends and the recursion of C ends because it only had H. Okay, now it will take the third the third node in the for loop. So we finished B, we finished C, now D. Okay, visit D. To visit D, just follow it here. Visit D, print D. So we print D. We print D here. Okay. Now for each child of D, I have a recursion at I and J. So at I and at J, these are the recursions for D. So in the for loop, I have to visit I and visit J. So when I visit I, okay, visit I, print I printed I. Now for each child of I, there is no children of I, so we finished this. We finished with I, we finished with I, and now J. Visit J, we also print J, having no children, no for loop, so we finished J, and now all the iteration finished and all the recursion finished because the for loop, the first for loop that started with a pointer to A has finished because we finished B, we finished visiting C, and finished visiting D. So the function call ends, and this is going to be the output of the traversal. All right, so this is a normal recursion. Okay, this is a normal recursion. This is the implementation of the pre-order. So the tip here is that to visit the tree, so usually you visit the whole tree. I want to visit the whole tree in pre-order. So to visit the whole tree in pre-order traversal, first we visit the root. We only visit the root, and from the root there's a recursion to all the children. In which order you print or visit, you do the operation on the root, on the parent, and then on its children. And for each child, you do the operation on the parent, then on its children, on the parent, and then on its children. All right, please, you have to actually implement this and send it to me in an example. So the first step is that you are going to create the tree. Okay, so you have to create. If you need any help, you can use the lab. So you have to create the tree. To create a tree, you have to have a node. Okay, your node will contain a pointer. Okay, and a pointer to the node. Okay, and a value. So you have to have a pointer to the node. Inside this node, you have a value, which is the value, let's say in this case, it's a character A, and a linked list of its node. If you find any complexity, please let us know. This is another pre-order example. So you visit the parent, you start by visiting the root. So by visiting the root, you have to visit all the nodes of the tree. So visit the root, you call function visit root. So it will print root. Then it's going to have a for loop on all its children. In the for loop, I'm going to visit the child as if it is the root of this subtree. So I have printed, and then I look at this child in the for loop. It has two children, which are lecture and homework. So first we visit root, so you print root, we print CC413, then we print lecture, then homework, then the second child, for the second child, CC231, then its children, and finally the last child doesn't have any children, so this is going to be the output of the print sequence for this tree. You should be able to actually do a pre-order on any tree that I give you. Now, if we look at this, some compilers use pre-order in their calculation. Okay, and this is how this is the syntax of what they use. in the semantics of doing the operation. So what they do is they do a pre-order traversal of such a tree, of an expression tree. This is how it really looks like when you write it down, but how it's traversed is in this way. That would be the analyzer in the compiler. Okay, so this is a pre-order traversal. How does it do it? So start with the root, parent, child. You can follow it and you will see that it's following this correctly. You will see these things in your compiler course. And that's why we have to understand when I say pre-order traversal, you should know that it visits first the parent child and then the parent node and then its children. Now, what about post order? As I said, post order, first you print, first you finish with all the children. So first you finish with the children and then you do the operation on the parent. So in this case, for example, the last thing is printing the root, okay? And we do it recursively like before. But as you can see, first you do the for loop and then you print the node. And in this case, you are assuring that you go through all the children and you print all the children before you print their parents. So for example, here you have A, so visit A, use A. In this case, we use the verb use. You could have used another function name, you can use any function name. So use A. So let's say we're printing, in this case we're printing. So to use A first, what do? For loop through its children, through B, C, and D. And it's a for loop for each children. So first you have to finish with B, then C, then D. To finish with B, also you apply post order. So I'm going to have another for loop that's looking at its children. Before I print B, E, F, and G. E, F, and G are also treated as if they are subtrees. So I have to look at their children. Okay, E doesn't have a child, so the for loop, this for loop will be empty, and I go ahead and print it. So we print E. And this is E, F, and G are in the for loop of the call of visit B. So in the call of visit B, I have a for loop on E, F, and G, which are its children. Finished with E, I go to the second child because for I have E, F, and G. Now in the F, finished with E, I go to the second iteration in the for loop F. Okay, I have to use F, you have to call the function, but F doesn't have any children, so again this for loop is empty, so I print it. I go, skip this one and go to print F, so I print F. Okay, still in the for loop of the B, of use B. Now I have G, I still have the child G in the for loop, I visit G, use G. In use G, I have to go through the children of G, but G doesn't have any children, so there's no for loop. The for loop is not going to be applicable. I go to print and print G. Now I finished the for loop of B, of visit B, because I finished at E, F, G, I finished it. It had 3 iterations. Every for loop has a definite number of iterations. So I finished E, F, and G. Okay, now this one is finished for B. So what do I do now? Print B. So I print B. Now I have finished the first iteration of visit A because I finished B. At this point, I finished B. In the for loop of visiting A, I finished the first iteration, which is B. The second iteration of the for loop is C. So I visit C. To visit C, first of all, I have to loop through its children. Okay, it has one child, H. Visit H, use H, but H doesn't have any children. Loop through its children, no children for H. So print, so I print H, here it is, print H. Okay, finished with H, which means I finished with the for loop of visit C. Finished, I finished for loop of visit C. So print C, I print C, here it is, printed. And now I finished this iteration for the use A, I finished B iteration. So for loop had 3 iterations for A. For C, it had 1 iteration, which is on H, finished it. So I finished B, I finished C. Now I'm still in the for loop of use A. Now visit D. All of you have taken a recursive call, and this is a recursive function. You should be comfortable with it. So before you go on to the next step, you have to finish all the iteration, all the recursion. So visit D. In visit D, there's a for loop. Use D. You have a for loop. You have to for loop through the children of D. I have I and J, so I have a for loop, iteration on I, on iteration of J. The iteration of I, use I. For each child of I, there is no children of I, so we skip this one, print I, so I print I. Okay, finished with I. In the for loop of D, I still have to visit, I still have another iteration, one on I and one on J, because for all children of D, finished with I, now with J. For all child of J, no child for J. So we continue to print J. So I print J. Now I finished the for loop of D. I loop through the iteration. I finished iteration of I and iteration of J for D. So I finished the for loop for use D. What do I do now? Print D. So I print D. At this point, for loop of calling use A has finished. We have finished all the children, all the iterations of the for loop that was on B, C, and D for the root for A. So having finished the for loop, now what do I do? Print node, which is in this case A, and the recursion ends. Okay. This is post order example, and again, I want you to implement it in the lab. And whenever you have a tree, you should be able to do pre-order and post-order. So the print sequence is what? You print, so we said, we print children first, then parents of the child is this one. Okay, so we start with lecture. Then the desk child, which is homework. Okay, so we finish with the children. This is the for loop. Then the parent. Okay, that's how it goes. Lecture, homework, parent. Okay, then the next child. We don't print it, we print its children. So lecture again. Then the parent of this child. Very smart there. So then the parent. Okay, then this child. And because it doesn't have any children, and finally the root. You should be able to do post order and pre-order. Very simple. And you will see that the first example that I gave you, which was writing the expression, it actually used in order. Okay, but you are not responsible for in order. In order was you do the left child, the parent, and the right child. So in here, we're just going to take post order and pre-order. So what we have taken so far is how to add to a tree, how to delete from a tree, how to traverse a tree, whether pre-order or post-order. And you are supposed to do those in the lab, in the assignment. You have to send it to me and to Miss Hoda. Now, as I said, these trees were actually didn't have a specific type. However, we have specific types of tree. In this example, in this case, what we'll see now is binary tree. What is a binary tree? A binary tree, as you can see before, we had the option of having a parent with more than one child, with 3 children, 4 children, 5 children. In this case, in a binary tree, we can have at most 2 children, at most. So in a binary tree, you can have at most 2 children, which means you can have 0 children, 1, 0, 1, or 2. So in this case, you call it a binary tree, and binary comes from having 0, 1, or 2 children. We have another type of trees, which are the complete binary tree. In this case, a node can have 0 or 2 children only. So as one where a node can have either 0, which means it's a leaf, or 2 children. So if it's a parent, then it should have 2 children, or else it will have a leaf. Okay? So a complete binary tree is one where a node can have 0, which means it's a leaf, or else it should have exactly 2 children, and all the leaves should be at the same depth, which means a complete binary tree should always, let's say, look like it has a certain shape. For example, in this case, this is an example of a complete binary tree where all the leaves are at the same level. It's a very organized tree. Excuse my writing. Okay. So a complete binary tree of n nodes has depth. So a complete binary tree in this case has a depth of big O of log n. Okay, and depth is, like you can say, it's the number of edges in a tree from the root to a child. Okay, so the one I drew a minute ago, this one, it has a depth of 2. Okay, and how many children does it have? 1, 2, 3, 4, 5, 6, 7. Okay, 7, which is 7 is considered 2 power 4. I mean 2 power 2. Okay, not 2 power 3 because it's less than 2 power 3. So it's the floor of 7 of log 7, which is going to be equals to 2. Okay, so as if it's 2 power 2, so it's going to be log n, which is 2. Again, a complete binary tree of n nodes has a depth of big O of log n. Okay, so in this case, it's going to be 2. This is the proof. Okay, so prove by induction that the number of nodes at depth d is 2 power d. All right, so I want to prove that